Alright, we are now in part 4, the last part of our discussion in electrochemistry. So this is on the application, specifically the batteries, the different kinds of batteries. So a battery is actually a galvanic cell or a series of connected galvanic cells that can be used as a self-contained source of direct electric current. So the two most common that we see at home, we have the dry cells and the alkaline batteries. So both actually involve zinc, manganese oxide, and the electrolyte. So both gives around 1.5 volts. Okay, so the dry cell, uh, 1.5 volts. The alkaline cell also, it gives you this around 1.5 also. The electrolyte here used is of course, the hydroxide. It's an alkaline, it's a base. Okay. Another type is the lead acid batteries. This is in our cars. This actually is made of 6 identical cells in series, and each of these delivers around 2 volts. So the lead anode, so our anode is the lead, and then lead oxide is our cathode, that is immersed in sulfuric acid. So lead is our at the anode and lead oxide at our cathode. So this is the overall um, reaction. So this is a rechargeable. So this battery discharge uses sulfuric acid. And another kind of battery also is the solid state lithium battery. So we often have this in our phones, in our laptop, and this gives relatively large potential. So this is usually around mga 3.4 volts, and this can be recharged hundreds of times. So at the anode is our lithium, and at the cathode it could have different kinds. Uh, in here, at the cathode, it's titanium. And then there's also the fuel cell. So um, this is also an electrochemical cell that requires continuous supply of reactants to keep functioning. So this will give us direct production of electricity, and this is very efficient because um, the only waste product here is water. So we have the reaction at the anode, and then the reaction at our cathode. So basically, it's just production of water. So another important application of electrochem is the concept of electrolysis. So actually, this is electrolysis is the use of electrical energy to drive non-spontaneous redox reaction. Example is the electrolysis of molten solid. So let's say here the electrolysis of molten sodium chloride. So what happens here, at molten state, the ions can move freely. Okay, so this actually involves inert electrodes. So like here our carbon anode. Okay, the what happens here, the anions move towards the anode at our oxidation site, and then the cations move towards the cathode at the reduction site. So um, we extract electrons from chlorine. No? So we extract electrons from chlorine and force electron into the sodium. So these are our equations uh, for the cathode and then the anode. So for this reaction to proceed, we must supply at least 4 volts from a battery. So the E cell here, the E cell, since this is electrolytic, so it's a negative. So it's negative 4 volts actually. So we need to supply at least 4 volts for this to proceed, and it's usually from a battery. So let's focus before we go to the quantification. There's also electrolysis for liquid or electrolysis reactions in aqueous solutions. This is much more complicated than the molten salt electrolysis. Here, the electrolysis of water, so basically the product, the overall reaction is your water breaks apart into oxygen gas and then hydrogen uh, gas. So we need to some limitation for electrolysis reactions and aqueous solution, just like in water. We need to add an electrolyte, so usually sulfuric acid, to provide enough ions to create a current. Uh, to create a current. So let's proceed now to the quantitative applications of electrolysis. So what happens here, the current that you need. So remember, we need to supply a particular current for the electrolysis to take place. And for the electrolysis to completely happen, we also measure the time. So remember, when you multiply the current, which is in ampere, then with the time, so that gives us the charge, which is in coulomb. So we can uh, determine the amount of the product form, meaning here the amount of the product form of the electrolysis, based on the amount of the electrical charge that passed through the wire. So in other words, the amount of the product form is directly proportional to the amount of electrical charge passed through the wire. Okay, so again, you can just easily follow these steps in the calculation. So from just multiply the current and then the time, we get the charge, and then we divide using the Faraday's constant in order to get the mole of electrons, and then convert into mole of the substance, and then into grams. So remember, the mole of the electron, that's equivalent to 96,500 coulombs. So here's the sample problem. How much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 ampere is passed through the cell for 1.5 hours? So again, this is what happens in our anode, chloride. The Cl- is oxidized into Cl2. In our cathode, the calcium 2 plus will be reduced into calcium. So the calcium will be produced by electrolysis. So that's the overall equation. So the number of electrons involved is actually 2 moles electrons per 1 mole of calcium. So we multiply, we get the mole of calcium. First, we need to the current, no? So 0.452 in ampere, we convert that into coulomb per second. So ampere is just equal to coulomb per second. Remember, we have ampere times second is equal to coulomb. Okay, so ampere is just equal to coulomb per second. So we multiply the number of hours and then convert into seconds. So we get the remaining unit now is coulomb. Then we use the Faraday's constant, 1 mole of electron. It has a charge of 96,500 coulomb. So we now have mole electron, and then we convert that based from the equation. Per mole of calcium, you have 2 moles of electrons. So we cancel. So what we get is 0.0126 mole. Then you can convert that into grams. Just multiply it with the molar mass. So we get 0.50 grams calcium. So if you pass through a current of 0.452 amperes for 1.5 hours, so the amount of calcium that will be deposited is, or that will be produced, is actually 0.50 grams. 0.50 gram. Okay. So another application, important application for redox is the corrosion. So corrosion or rusting is just the deterioration of a metal by electrochemical process. So what happens here? So let's say your stainless steel, which is made of iron. So at the cathode, it's basically because of the oxygen, no? So from the air, no? From the surrounding. So the oxygen gives you water, and then at the anode, it converts the iron solid into iron 2 plus, and further it oxidizes into iron 3 plus, creating what we call as the rusts. So rusting is a electrochemical process. So to prevent corrosion, there is a process called passivation. So it's a formation of a thin oxide layer by treatment with an oxidizing agent. Um, we can also form alloys. For example, stainless steel, combination of several metals. And then we can coat with a layer of less active metal like tin. Or we can have cathodic protection. So we use zinc or magnesium as the sacrificial metal. So we coat uh, the layer with zinc or magnesium. So what happens, the zinc and the magnesium would react first before the iron can undergo redox. So the zinc or the magnesium are considered as sacrificial metal, so protective layer. So these are some of the ways to prevent corrosion. Okay, so that ends our discussion in electrochemistry.